this video, we'll cover the problem shortest path on struct. For this problem, we'll be given a node A and a node B, and then we're going to be given the edges of an undirected graph. And we want to find the length of the shortest path between node A and node B in the given graph. If there is no path between node A and node B, we should be returning -1. And I believe that should be all the details. One other detail is we want to count the number of edges in the path, not the number of nodes. I'll talk about why that's important in a moment. Now we know that we can use a breadth-first search or a breadth-first traversal of our graph to find the shortest path. Because first we visit all of the nodes that have first we visit ourselves. After that, we visit only nodes that are within one edge of us. And then we only visit nodes that are within 2 edges of us, and then we only visit nodes that are within 3 edges of us, and so on. So the first time that we ever find our target node, we know we have used the shortest path to get there. But we need to actually track the distance that we are traveling. So every time we traverse one edge, we want to increase our distance by 1. And so we can use our breadth-first search to do so. Now, the key before we can write our BFS is whenever we're traversing a graph, we want to know how to get from the current node to the set of neighbors that are connected to our current node. The easiest way to do that is to have an adjacency list. That's going to be a hash map that takes in some node as the key and maps to an array which contains all of the neighboring nodes to that initial or current node. What we're going to do to get us started is we are going to build a graph. I'll write a function called buildGraph that takes in an array of edges, which is what our actual input is, and returns an adjacency list. So we'll have our function, we'll use an arrow function, it takes in the edges. Now we know we're going to have a graph. I'll use a JavaScript object here so that we can map whatever our keys are going to be, which will be each of these nodes, which are strings, to an array of their neighbors. Then what we'll do is we'll iterate over each edge. So for each edge of edges, we'll grab node 1 and node 2 using some destructuring here. Now, the easy way to do this is we can just say, if we just assume that we already have an array that exists, we can just say go to graph at node 1, which basically is like the neighbors of node 1, and push into it node 2. And we can do the same thing for the reverse direction. So we can say go to graph at node 2, which is the neighbors of node 2, and then push node 1 to say, hey, there's a neighbor here. But the key is that sometimes we don't have these arrays. Graph at node 1 in the very beginning is just nothing. It's undefined because node 1 is not in our graph. So what we'll do is we'll say, we'll have a Boolean that'll be like node 1 in graph is going to be graph.hasOwnProperty. This is important. Whenever you're checking if a JavaScript object has a certain key, you should be using the function hasOwnProperty instead of something like the keyword in, or just checking if graph at node 1 is undefined. The reason is because graph.hasOwnProperty is the only way that will not, or like the only way of checking a key that does not check the prototype. So there are certain methods that are always on the prototype. So for example, let's see, I think constructor is a common one. So if you were to check something like constructor in graph, this would return true always. I'm assuming that this is one. Or even we could do hasOwnProperty. I know for a fact that's a key. This would return true even though you never set a value for hasOwnProperty, because the kind of prototype, the root of a JavaScript object, always has this property. When you invoke the hasOwnProperty method like this, it specifically checks for keys that you have set, not things that were set by the prototype. So that's why it's really important to make this check in the correct way. Now, what we can say here is if node 1 is not in graph, we simply add it to the graph and set it to be an empty array so that we can push over here. And you can imagine the same logic will be done for node 2. This is very standard logic and is done for very commonly and frequently for problems where we have an undirected graph or even a directed graph that is given as an input of edges. Okay, now we can go ahead and write our BFS logic. So the first thing we'll do is we're going to use a queue. Struct doesn't have like a built-in queue class. We're going to use an array. And whenever you write an array, you should be writing a comment explaining that you know that this is not the optimal way to implement the solution to a BFS or any sort of use of a queue, because remember that even sometimes, like the hiring committee at Google, for example, will see your code, and the interviewer may have not taken down a note of the fact that you understand that this is a suboptimal implementation. So you want to be very precise about this. So I would say, in practice, I'd use a real queue for O of 1 dequeuing, but for the sake of this interview, I'm using an array. Okay. Then, in our BFS, what we want to do is we want to push onto our queue the kind of starting node. So we'll just BFS starting from node A and wait until we hit node B. Or that's arbitrary. It doesn't have to be that direction. It could definitely be the other way. So I'm going to have the node, which is going to be node A, and then we're going to also have a distance we've traveled so far. Now here's the key. So I'll name this distance so far. Note that we want to count the number of edges in the path, not the number of nodes. So for example, imagine we had a path that looked like this. A to C to D to B. And let's say A was our starting and B was our ending. You could say that this path has a length of 4 because we have A, C, D, B, that's 4 letters. Or you could say there was 3 arrows, like 3 kind of times we transition between nodes. Sometimes in a problem, they're asking for the number of nodes in the path, so this would be 4. Sometimes they're asking for the number of edges, so this would be 3. So you have to be careful with how you track this data. In this problem, they're telling us that they want the number of edges, so we should be returning 3. So, when our path only contains the first node, we'd wonder how many edges we have. Well, we have no edges, because it would just be A, no arrows. So we'd start with a distance so far of 0. Now, there's one other thing you should be asking yourself whenever you're creating the queue, which is whether or not we need a visited set. And whether or not we need a visited set is determined by whether or not there can be cycles in the graph. If there can be cycles, for example, imagine you can go from A, oh man, I don't know what they're doing. Okay, yeah, that's what I'm looking for. If you can go from A to B and B to A, then we would just infinitely go back and forth. We go from A to B, we go back from B to A, and then A to B, and then B to A, and this would just continuously go forever, and there's no point in checking that path. It's not useful. So what we do is we mark things that are visited and say, hey, don't visit this in the future because we've already visited it. So then the question becomes, can we have a cycle like this where we can go back and forth? We have an undirected graph here, and at any point in an undirected graph, you certainly can have cycles, because you can go from one node to another node and then back to the original node. That is the definition of an undirected graph. So, if you're ever working with an undirected graph, you need to make sure you're careful about how you're handling visited data. So, what we'll do is we'll create a set to track what nodes we visited. And in the beginning, we're going to say, hey, node A has now been visited. We don't ever need to add it to our queue again. Once that is done, we'll write our while loop. So long as there are elements in our queue, we want to do 3 things. We're going to remove a node. We're going to process the node. And then we are going to add the neighbors of that node to the queue. Removing the node is pretty straightforward. I'll just use some destructuring here. So we'll just do queue.shift. Now remember, this is O of n time in an array, but if you had a nice efficient implementation of a queue, it would be O of 1, which certainly can be done, and in practice you will usually write your BFS this way. Now we have the node and the distance so far that are the keys of our object. The process node step we will come back to in a moment, and we'll think about what we want to do there. But for the add neighbors, we want to get the neighbors of the current node. So we can do neighbors is going to equal graph at the current node. That's how we defined our graph. It's an adjacency list where the key is a node and the array is a list of neighbor nodes of the key node. Now, there could be a case where... Actually, no, never mind. I don't think that case will ever show up. I was thinking sometimes node cannot be present in the graph and we have to check for that. But I believe in this problem that should not happen. If it does, we'll see when the tests are making a mistake, and then we can add that check. But I believe it won't be necessary. Okay, then we can say for each neighbor of our neighbors. And remember, the neighbor is just going to look like a string. It's like a node, and in our case, nodes are just strings. So we can add the neighbor to the queue. But before we do that, remember we just talked about cycles. We need to make sure that the current node is unvisited. Otherwise, we're just going to go back and forth all the time. So we can say, if the visited set already contains our neighbor, we should just continue. Otherwise, we can add it to our visited to make sure, hey, don't ever add this to the queue again. And then we add it to the queue. And here we have to make sure that when we push to the queue, we use the same data type as above. So if you're using an object here, you need to use an object down here with the same keys and values. With the same keys. So node is going to be our neighbor node. And then our distance so far is going to be the distance so far of the current node plus 1. Remember that we're counting the number of edges. So every time we take the edge from the current node to a neighbor node, we need to mark that fact and say the distance has increased by 1. The number of edges in our path has increased by 1. So this is the key logic that allows this algorithm to work for the current problem. Now, the last question we need to answer is, what do we do with the process node step? So the process node step answers the question of what work do we want to do for each node. And in this case, it also is helpful to think about what is the goal of the problem, especially for shortest path BFS problems. The goal of the problem is to find the shortest path between node A and node B. So the way that we know that we have finished is when we find node B. So what we can write is we can say if node is equal to node B, we've done something, we're done. And what is our goal here? Well, we want to return the distance, the number of edges. So whenever we find the target node, we should return distance so far. This is the core logic for what we want to be doing. At every node, we want to check, am I at the end? If I am at the end, return my distance. And so that's what's going to go in the process node step. Now, there's one last thing we want to handle, which is that if there's a case where we never return right here from our BFS, then we're going to come out here, and that's just by default, JavaScript is going to return undefined. But that's not what we want. If we break out of the while loop, it means we never found node B, which means that from node A, there is no way to get to node B. So we need to handle that. We can return -1, which is what they asked us to return here. However, this is not very meaningful. As a human, if you look at return -1, it doesn't really make sense here. It's like, okay, the length was -1. This is just not very clear. What we can do is, this would be like considered a magic number, right? There's just kind of a number that arbitrarily appears in the code. And as a human looking at it, it's not clear what that means. So what we can do is we can declare a constant to name that magic number. And so when you see it in code, it's a lot easier to look at. So we can say no path between A and B is going to equal -1. Then what we do is we return that number. So you can see we're still doing what they want us to do. We're returning -1. But when a human sees this code, it makes a lot more sense. They can see, okay, if we break out of the while loop, it means that there was no path between A and B, and then we return no path between A and B. Okay, now I believe that should be all the code for this problem, so let's go ahead and run it and see if we are missing anything. Great, okay, looks like it passes all of our tests. Okay, that's all for this video, and thank you for watching.